Hello, everyone. I'm Swarun Kumar from Carnegie Mellon University. It's my pleasure to present to you today the very first session topic preview for ACM MobiSys 2021. And the session is titled Mobile Communication. Mobile communications has been at the heart of the ACM MobiSys community. Now here below, I have a word cloud of the keywords across different editions of ACM MobiSys. And you can see the word mobile and the word communication, along with several other related words like networking, computing, devices, architecture, systems, and so on in the word cloud. Now, I want to flash back to MobiSys 2011, exactly a decade ago when I was a PhD student myself. And I want to tell you about the important concepts and keywords when MobiSys was presented then. And unsurprisingly, Wi-Fi and cellular ruled. You can see that in the word cloud over there. This is unsurprising. Smartphones had widely proliferated, become extremely popular. There you see a picture of iPhone 4S that was released in that very same year, 2011. Of course, unsurprisingly, my PhD was also around Wi-Fi and cellular, making it faster, building new services, localization, and so on. But cutting to MobiSys 2021, the story is a lot more complicated. Here's a word cloud for the keywords in this session today, and you can see quite some variation. The biggest, most popular words are systems and platform, which are not quite informative. But looking deeper into the smaller words, we see millimeter wave, LiDAR, dynamic, BLE, next generation, interference. We see all sorts of new and different concepts. So it's a lot more of a heterogeneous ecosystem. In fact, the papers in today's session span many different topics, ranging from 5G, millimeter wave, RFIDs, Bluetooth, visible light communication. So the wireless landscape has become significantly more complicated. So let's sort of contrast the MobiSys communications challenges, contrasting the year 2011 and 2021. Now the problems in 2011 were quite familiar. At that point, we wanted faster Wi-Fi, we wanted faster cellular. Of course, Wi-Fi and cellular ruled the roost. We, in other words, wanted more speed. Now, of course, this was also influenced by things like scale, interference, and so on, that we also wanted to optimize essentially to get higher speed. And the speeds we were talking about were in the order of maybe hundreds of megabits per second for wireless networks. Now, cutting to 2021, though, we still want faster speeds for, again, Wi-Fi and cellular, but this time, when we say speed, we mean several gigabits per second, and we are talking about technologies like millimeter wave and beyond. But of course, none of this is set in stone. Technologies like millimeter wave, and in fact, even sub 6 gigahertz has problems, and which we'll talk about that when we talk about the papers in this session. Also, at the same time, we have this new heterogeneous landscape that's emerged from the Internet of Things. We want new solutions to connect the Internet of Things. And that's another trend that's, again, on the upswing in 2021. So if you look at the mobile communication landscape in 2021, we can broadly say we are optimizing for two things. One, for faster communication with technologies like millimeter wave, but even sub 6 gigahertz, with important pain points being bandwidth, steering beams when it comes to millimeter wave, programmability, bringing up new hardware that's more adaptable and programmable. And on the Internet of Things side, we have pain points like dealing with the low power of devices like RFID tags, Bluetooth, low energy devices, and so on, as well as the sheer scale and cost when these are deployed at scale. Now, there are a few notable absentees in my mobile communications landscape list, but fortunately, these are covered by other sessions. So other than speed and scale, you might also want to optimize for latency. And we do have an augmented reality session where some of the papers do talk about optimizing for latency. Also, we're dealing with communications here, but there are other equally interesting applications that you can build on top of the communications network for sensing, localization, and human-computer interface applications. And we have sensing, HCI, and localization sessions that talk about these concepts. Also, more familiar other concepts like mobile applications, mobile machine learning have their own dedicated sessions as well. So I'd encourage you to check those out. But back to today's session, which talks about communication. And unsurprisingly, the papers in this session can broadly be divided into these two buckets chosen by me, faster communications and the Internet of Things. Faster communication here highlighted in blue and Internet of Things highlighted in red. And you can see that there's a fairly diverse set of papers from different research groups all over the world. So I want to focus for the moment on faster communications. I'll talk about the Internet of Things later. And I want to focus on 3 papers that deal with faster communication and better communication infrastructure. And I want you to note the keyword highlighted in red, millimeter wave, that is repeated across multiple papers, including the second paper, although it deals primarily with sub-6 gigahertz. So you might ask, hey, what is millimeter wave? So much of wireless communications and mobile communications history has sort of dealt in the sub-6 gigahertz band, where it was easier to deploy and build communications hardware. Things like AM, TV, FM, cellular, satellite communications, and of course, Wi-Fi. And there's a good reason for this. It was inexpensive to build hardware. It's in the sweet spot where you can have tiny antennas and long range. But there's a challenge. Every year, data traffic and demand for data traffic is increasing by 53% year on year. And at some point, the bandwidth we have available in these bands will simply not be enough. And we already seem to be hitting that limit. And so it's natural to think, where do we go next? And it turns out there's all this vacant space, seemingly vacant space at higher bands than 6 gigahertz. So why don't we start there? Specifically, why don't we move to millimeter wave frequencies, traditionally above 30 gigahertz, where bandwidth is much more available, the open unlicensed bands, as well as cellular and other bands that have been given out in these at these frequencies. Now, the challenge and advantages are plenty when it comes to millimeter wave. On the good side, we have, because of Shannon capacity theorem and the higher bandwidth, we can support gigabits per second of speed. So our speed problem sort of goes away. But there's also a flip side. To get this speed and to get sufficient range, because millimeter wave decays much more quickly, there's one approach that you can do, which is to direct the beams using very sharp directional beams. Now, directional beams can be a good thing because they can allow for spatial reuse, which means, hey, multiple users can each focus, direct their beams to their intended targets. And this way you mitigate interference. But there's also a flip side, a negative because of directional beams. Mobility, even tiny mobility of your receiver could disrupt the network if you don't quickly adapt your beam. Also, if there is something that happens to block the direct path between you and the target, blockages can kill the link. So we therefore need platforms that are more resilient to mobility, more resilient to blockages, and also programmable platforms that can enable the next generation of millimeter wave protocols, because much of our programmable platforms have primarily focused on sub-6 gigahertz, unsurprisingly, because those have been more popular until now. So when I say directional beams, I literally mean beams of RF energy that are essentially created by things like phased arrays or directional antennas, as shown in the picture. So I'm going to talk first about a system called SpaceBeam, one of our papers today, that is a LiDAR-driven one-shot millimeter wave beam management system. And the key pain point that it addresses is this problem of beam steering for millimeter wave. Because remember, prior to communication, a millimeter wave transmitter needs to select the optimal beam using which it can deliver information to the receiver. But selecting this beam can often be time consuming. You often have to sweep through all the possible beam configurations, of which there are often many. And remember, millimeter wave is not just supposed to be high speed, it's also supposed to be ultra low latency for applications like autonomous vehicles, augmented reality. So you don't want to have a time consuming beam selection process prior to establishing every single communication link between all pairs of possible transmitting receiving devices. So their approach, very briefly in a nutshell, is to use LiDARs, which are an imaging modality. Effectively, what LiDARs can do in principle is generate a 3D visualization, a 3D point cloud of scenes such as this one, to know the exact location, depth, XY coordinates of various points of objects in the surroundings. And so can we use information from LiDARs to better inform get better information about the environment we are in, and as a result, perform better millimeter wave beams management and beam steering. That's really the principle behind the SpaceBeam paper, but for more details, I'd ask you to hear the presentation. We also have another paper in the millimeter wave space, this time addressing a different pain point. The paper titled Real-Time Experimentation Platform for Sub-6 GHz and Millimeter Wave Mining. Now, the pain point that this paper addresses is that today's software radio platforms primarily do sub-6 GHz. So platforms such as the USRP from National Instruments and other such software radio platforms in general don't delve too high beyond the 6 GHz limit. There are also a few millimeter wave software radio platforms that have been proposed, but these are generally narrower in bandwidth, and these are also generally harder to find and harder to scale. But more importantly, there is a lack of an SDR platform that can do both simultaneously, for example, for dual band operation. And that's precisely what this paper does. It built a first of its kind dual band programmable radio that operates both in the sub-6 GHz bands as well as in the millimeter wave bands. And they've actually built this out, they've tested it, and they've made it open and available to the community. And I encourage you to find out more about their system when they present their paper. Now, at this point, I want you to not forget that sub-6 GHz is also an equally important space, and most of 5G is happening around sub-6 GHz. So it is important to also build smarter and better systems that work here. And one solution that to this effect is the third communications paper in the session, which is called Scope, an open and softwareized prototyping platform for next-G systems. The pain point that Scope addresses is that there is an urgent need to develop open tools for next generation cellular systems. So with the advent of technologies like Open RAN, not just is the core network being more softwareized, but the RAN itself, the radio access network, that's traditionally considered to be closer to the user and in the base stations and so on, that is also becoming increasingly softwareized. And so when you're deploying these new solutions, it's important to have a sort of a safe test bed or emulation platform to first try out your solution before launching it on the field. And Scope is one key solution to making that better. And in a nutshell, what Scope does is it sort of sits on top of emulation platforms and prior test bed platforms, for example, the power test beds like Cosmos or Powder, from which it can effectively run sort of a layer on top to both configure these networks, but also collect valuable data. And this data can be pivotal for artificial intelligence and machine learning algorithms that can then be tuned accordingly based on the data collected by this platform. So I would encourage you to read more about Scope online and attend the presentation. Now, besides the faster communication sort of theme, I also want to highlight the other theme that we see in the mobile communications session today, which is the Internet of Things. Now, there are diverse technologies encompassing the Internet of Things. Technologies like LoRa, NB-IoT, Bluetooth Low Energy, Zigbee, Z-Wave, RFID, and so on. And the broad mandate of all of these technologies is to connect everyday objects around us, maybe notebooks, maybe credit cards, maybe even a cup of coffee or your shoes, perhaps. Right? What does it take to connect everything to the internet? And what are some technologies that can do it that are cheap, low power, cost effective, as well as scalable? Right? And so in today's session on the Internet of Things, or IoT for short, we have two papers that look at two different directions for IoT, one using visible light communication and the other using backscatter technology. So let me give you a quick preview of what is meant by visible light communication. So visible light communication is a broad class of technologies that have some sort of light source talking to some sort of light detector. In the case of this paper, the light source is an LED that's flashing and can change colors and so on. And the receiver on the other side is a camera that's detecting the LED, and therefore you have a communication link. And in the context of this paper, they're using it for communication between vehicles in the network and create a vehicular network. But there are also other contexts where visible light communication is used. For example, instrumented smart light bulbs indoors. It's also used in completely other contexts like free space optics for data center communication, for instance. So in this paper, they want to deal with visible light communication for fast moving objects like cars, for instance. And they want to address one challenge that is important when you want to have cars connected using visible light communication in an interference-free way, which is it's quite possible that you can have a very simple communication link between a single transmitter and a receiver on top of two cars on a visible light and create a visible light communication link. But in practice, you can have interference from other things, other sources in the environment, like other cars, when you have a bigger network of all sorts of other cars that also exist in the network. Now, one reason for this is that often to make visible light communication practical, you need your receiver to have a wide field of view. The reason is that your transmitter, the blue car here, might be moving around in different locations as it changes from lane to lane. And so to pick up those moves very quickly and not lose sight of the transmitter, it's important for the receiver to have a large field of view and observe almost everything in the surroundings. But in the process of doing that, it's going to experience interference from other cars. Now, in an ideal world, you just want to have a narrow field of view towards a transmitter. But hey, this means that if your transmitter moves, car changes lane, or the car swerves a little bit, then you might lose sight of the transmitter and your communication might be disrupted. So what RayTrack does is it has a dynamic field of view system that adapts very quickly between narrow and wide fields of view so that you can maintain good communication quality and detect and track the transmitter over time. And you can find more details of how they achieve this in their paper. Now, the other paper in the session deals with a very different IoT technology called RF backscatter, which arguably is even lower power than visible light communication because it's battery free. Now, you might have heard of RF backscatter in the concept of RFID tags, like the one shown here. Now, these are also found in things like your bus passes when you tap onto what is effectively an RFID reader, whereas the tag, like the one shown on the left here, is within the bus pass that you hold. Now, traditionally, RF backscatter harvests energy from a dedicated reader like this one, but there's been a lot of interesting work recently on harvesting energy from other sources like Wi-Fi access points, for example, or Bluetooth transmitters. So today's paper, last paper, talks about harvesting energy from Bluetooth or BLE and backscattering BLE communication. Now, the pain point that it addresses is that current systems for Bluetooth backscatter have relatively poor packet error rate and are not sufficiently reliable. And their system uh, builds a novel modulation scheme that exploits a combination of modulating frequency and phase along with different pulse shaping filters that significantly improves the reliability of BLE backscatter. And I encourage you to read their paper to find out how they achieve this performance improvement. So taking a step back and revisiting the mobile communications landscape, we've sort of seen two interesting broad visions across the papers for this session on faster communication, faster Internet of Things, using, among other things, a couple of very interesting and prominent technologies, millimeter wave on one end, backscatter on the other end. And it's tempting to ask, are these two separate themes, or are there interesting research directions that sort of blend the two? And so this is a good segue into some of my research. We had a paper in MobiSys last year on using millimeter wave backscatter for a very unusual application called tire sensing, where we wanted to sense the tread depth of tires, which if you own a car, you've done pretty often using a quarter or a penny of some sort to find out exactly how much your tire has worn out. Unfortunately, it turns out that tire-related accidents are one of the most common automotive accidents and leading cause of death globally. And so we wanted to do something about it, and we wanted to reuse a millimeter wave platform that already exists in your car, which is the millimeter wave automotive collision radar that usually is used for things like lane assistance. And we want to use these radars as RFID readers and strips of metal layers. And remember, metal is often already present in your tire as tags, and effectively find out how much tire tread has worn out over time, and also build more complicated images of tires. Right? There are many advantages of this. We can get continuous measurements. We can measure it at very precise accuracy to measure tread depth at sub-millimeter accuracy. We are resilient to debris, things like mud that stick on the tire, and metal is already used in the tire manufacturing process, so this is fairly easy to manufacture. And so this was a collaboration with Bridgestone Tires. Here's the millimeter wave radar platform that's attached to the well of my car's tire, and you can sort of see the different tire tread patterns that were sort of imaged using our algorithm. We also have a follow-up this year at MobiCom on using millimeter wave backscatter for a more general purpose application, which is location tracking for things like autonomous vehicles and augmented reality. And we built a very compact custom tag that can be tracked at centimeter accuracy at large distances, hundreds of meters away, using an ultra low power backscatter platform. And I'll encourage you to hear our talk at MobiCom. But I hopefully convinced you that mobile communication is a very exciting area. My research lab, the YTech lab at CMU, deals with many of these topics, ranging from battery-free, millimeter wave that we talked about today, wireless localization, sensing, security, low power band. So a lot of topics related to MobiSys. So if you are interested in my research, just send me an email or follow us at our website. But back to our session today. I hope that you can join us for MobiSys 2021. We have an exciting program with different topics from communication, sensing, localization. But I hope that you particularly attend the session 1 on mobile communications, the heart of MobiSys, where we have diverse papers on topics ranging from faster communications in millimeter wave, sub-6 gigahertz, as well as solutions for the Internet of Things. So please join us at MobiSys 2021.